There's a version of the universe that lives in your head right now. Stars scattered across a dark sky, galaxies turning slowly like pinwheels. Space, vast, quiet, cold. And here is the strange thing about that picture. Almost none of it is accurate. Not because you were careless, because the universe actively resists being understood on human terms. Tonight, do something you almost never do. Look up, not at a screen, not at a headline, but at the sky itself. That darkness above you is not empty, and it is not silent. It is the oldest thing you will ever see. And for the next hour, we are going to walk through it together, slowly. The way you would walk through a cathedral. You have lived long enough to know that the biggest truths are rarely loud. They arrive quietly, at the edge of an ordinary evening. What you are about to hear are not opinions. They are measurements confirmed by instruments, tested by generations of patient minds. And by the end, the sky you have looked at your whole life will never look quite the same. A gentle word before we begin. There is no need to hold on to every number you are about to hear. No test at the end of this hour, nothing to memorize. Let the facts wash over you the way you would let music play. Some will slip past, a few will lodge somewhere and stay with you for years. That is exactly how it should be. This is not a lecture. It is a slow walk through the largest thing there is, taken in good company on an ordinary evening, with nowhere else we need to be. So settle in, get comfortable, and let us take the first step together. So let us begin where everything begins, with silence. Because the first thing you must understand about the universe is that its silence is a lie. Picture the space between the stars. In your mind, it is probably a perfect nothing, cold, black, still. For most of human history, that is exactly what the greatest thinkers believed. Empty space, they said, was the absence of everything. It turns out they were wrong in the most extraordinary way. The vacuum of space is not empty at all. It is restless. It trembles. At the quantum level, the vacuum is seething. Quantum field theory, one of the most tested frameworks in all of physics, tells us that particles flicker in and out of existence in fractions of a second so small they make a billionth of a second look like an eternity. They appear, they interact, they vanish. Physicists call them virtual particles, and though the name sounds like fantasy, their effects are real and measurable. The vacuum is less like a blank canvas and more like the surface of an ocean in a storm. Turbulent, alive, never for one instant truly at rest. In 1948, a physicist named Hendrik Casimir predicted that two metal plates placed close together in a vacuum would be gently pushed toward each other by this invisible restlessness. It sounded absurd, a force coming out of nothing at all. Yet decades later, in careful laboratory experiments, that push was measured exactly as he said it would be. The nothing between the plates was pressing on them. The emptiness had a texture, and there is more inside that silence. Spread evenly across every direction of the sky is a faint glow of radiation, a whisper left over from the birth of the cosmos itself. It was discovered by accident in 1965 by two engineers who thought their antenna was simply dirty. They cleaned it. They chased away the pigeons nesting inside it. And still the hum remained. What they had found was the afterglow of creation, the cosmic microwave background, and it earned them the Nobel Prize. So think about what that means for the space around you right now. The gap between your hand and the wall, the darkness outside your window, the void between the planets. None of it is truly nothing. It is full. It is humming with the leftover energy of the beginning of time. Energy so faint and so ancient that we only learn to hear it within living memory. The nothing you were taught to imagine simply does not exist. What looks like absence is presence in disguise. What looks like stillness is motion too subtle to see. And consider how young our knowledge of this really is. For thousands of years, every astronomer who ever lived looked up at what they were certain was empty blackness. It took until the middle of the last century for us to discover that the emptiness was singing all along. That should teach a kind of humility. The universe does not hide its secrets out of cruelty. It hides them in plain sight, waiting patiently for instruments delicate enough and minds curious enough to finally notice. We are the first generations in all of human history to hear that ancient hum. And it was there the whole time. And that restless vacuum may be doing something far grander than trembling. Many physicists suspect that the energy of empty space itself is what is quietly pushing the whole universe apart, growing stronger as space grows larger. If that is true, then the same nothing between your hand and the wall, multiplied across the unimaginable emptiness between the galaxies, becomes the most powerful force in all of creation. The smallest thing we know and the largest fate of everything may turn out to be the very same thing. Hold that thought lightly for now. We will return to it at the very end of our journey when we ask how all of this finally comes to a close. And if the emptiest thing we know is secretly this alive, you have to wonder what else we have gotten wrong. Starting with something far more personal. What it even means for the universe to be big. Before we can understand what the universe is made of, we have to confront something your brain will resist every step of the way. Size. Not the size of a mountain or an ocean or even a planet. A scale so vast that every unit you use in daily life simply evaporates. Let us start somewhere familiar and then walk away from it. Slowly, until familiar is only a memory. You are standing on Earth, roughly 8,000 miles across. Fly around the whole equator and you would travel 25,000 miles. It feels enormous when you are standing on it. Now look up. The moon is about 240,000 miles away, 30 Earths lined up in a row. The astronauts who went there said that watching our planet shrink to a marble in the window was one of the most overwhelming moments of their lives. That marble held every person they had ever loved, every city, every ocean, every war. A marble. The sun is 93 million miles away. Drive there at highway speed without ever stopping, and it would take about 170 years. Light, the fastest thing there is, crosses that gap in just over 8 minutes. Now go further. The next nearest star, Proxima Centauri, is about 4.2 light-years away, and a single light-year is roughly 6 trillion miles. Our fastest spacecraft, Voyager 1, launched in 1977, would need around 73,000 years to reach it, 6 times longer than all of recorded human civilization just to arrive at the nearest star. And that star is our neighbor. Our galaxy, the Milky Way, holds somewhere between 200 and 400 billion stars, and it stretches 100,000 light-years across. Travel at the speed of light from one edge to the other, and empires would rise and fall, ice ages would come and go, and you would still be traveling. Then zoom out again. The Milky Way is one galaxy in a cluster of more than 50. That cluster sits inside a supercluster called Laniakea, so enormous it would take 520 million light-years to cross, containing an estimated 100,000 galaxies. When astronomers pointed the Hubble telescope at a patch of sky that looked completely empty, a spot no larger than a grain of sand held at arm's length, they did not find darkness. They found thousands of galaxies. All told, the observable universe holds hundreds of billions of them, perhaps 2 trillion, and more stars than there are grains of sand on every beach and in every desert on Earth. Here is where I gently pull you back from feeling small. Yes, you are one being on one rock, circling one ordinary star. But you are also the part of all this that woke up and started counting. You are not lost in the numbers. You are the reason the numbers can be spoken at all. And there is a shape to all that vastness that almost no one expects. When astronomers map the universe at its largest scale, the galaxies do not scatter randomly like spilled salt. They arrange themselves into enormous filaments, threads of matter hundreds of millions of light-years long, with vast, nearly empty voids between them. Scientists call it the cosmic web. And here is the detail that makes people go quiet. Seen from far enough away, the structure of the universe looks strikingly like the network of neurons inside a human brain. Whether that resemblance means anything profound or is simply geometry repeating itself at every scale, nobody knows. But it is the kind of thing that makes you set down whatever you were doing and simply wonder. And here is the part of scale that most explanations quietly skip. It is not only that the universe is big, it is that the distances between things are almost entirely emptiness. Space is not crowded. It is not busy. Even in the denser parts of our galaxy, if you were set adrift at random, the nearest star would still be years of light travel away in every direction. The cosmos is overwhelmingly, achingly empty. And yet, against all that emptiness, matter somehow found its way together. on one small rock, circling one ordinary star, tucked into one arm of one galaxy among hundreds of billions, chemistry happened, life happened, you happened. That, against those odds, is no small thing. But the universe wasn't always this vast, this structured, this full of stars. There was a first moment, and we can describe it second by second, when all of it exploded out of something smaller than a single atom, roughly 8 billion years ago. Everything that would ever exist, every galaxy, every atom in your body, every particle of light that has ever traveled anywhere was compressed into a space unimaginably smaller than a single proton. Not metaphorically smaller, physically, genuinely smaller. A point so dense that the laws of physics as we understand them simply stop working. Our equations hit a wall, and that wall has a name: the singularity. Then something happened. Not an explosion in the ordinary sense, because there was no space for an explosion to expand into. Space itself began to expand. The Big Bang was not a bomb going off inside a room. It was the room itself growing, rapidly, violently, in every direction at once, with nothing on the outside, because there was no outside. In the first sliver of a second, the universe underwent what physicists call inflation, an expansion so fast that regions of space flew apart faster than light, not by moving through space, but because space itself was stretching. In those first impossible moments, the temperature was beyond anything you can picture, and the four forces we know today, gravity, electromagnetism, and the two nuclear forces, were fused into a single force. As the universe cooled, they split apart one by one, like a crystal freezing out of water. Within the first fractions of a second, quarks bound together into protons and neutrons. But the universe was still so hot that electrons flew free, and the whole cosmos was opaque, like trying to see through a wall of fire. This lasted about 380,000 years. Then the temperature dropped just enough. Electrons slowed, protons captured them, and the first simple atoms of hydrogen formed. Suddenly, for the first time, light had somewhere to go. It streamed outward across a newly transparent universe, and that light is the very same cosmic microwave background we met in the first chapter, the oldest light in existence, still arriving today. When an old television was tuned between channels, a fraction of that flickering static was this signal, the afterglow of creation appearing in your living room. And here is what is deeply strange. That ancient light is almost perfectly smooth, but not quite. Scattered across it are tiny ripples, minuscule variations in density, quantum wobbles stretched to enormous size during inflation. Those ripples became everything. Gravity seized them and amplified them over millions of years, pulling matter into threads and sheets and filaments. Every mountain, every ocean, every face you have ever loved traces its origin back to quantum noise in the first fraction of a second. Randomness, frozen into the structure of reality. But the young universe held only hydrogen and helium, the simplest atoms. To build everything else, it needed a furnace. And there is one more thing worth pausing on before we leave the beginning. People always ask what came before the Big Bang, and it is the most natural question in the world. But the answer is stranger than any story. Because time itself began with the universe. Space, matter, energy, and time all switched on together in that first instant. Asking what happened before is a little like standing at the North Pole and asking which way is north. The words simply run out. There is no before, because before is a word that needs time to exist, and time had not started yet. Sit with that one for a moment. It lands differently the longer you hold it. And the mathematics that describes this beginning keeps pointing somewhere even stranger, somewhere we have no way to visit. The same equations that predicted black holes, that predicted the bending of starlight, that have been proven right again and again when our intuition said impossible. Those equations hint that our universe might be only one among an unimaginable number. A vast collection of other universes, each perhaps with slightly different laws, different constants, different versions of everything that exists. We have no direct evidence, and we may never have any. But the math has earned our attention before, and it quietly suggests that the beginning we just described might not have been the only beginning of its kind. It needed something that could take those plain atoms and cook them into carbon and oxygen and iron, Something that would live and burn and die, sometimes quietly, and sometimes with a violence that briefly outshines a galaxy. From the time we are children, we are told that stars are distant suns, balls of gas, fixed points of light we use to navigate and make wishes upon. That description is not wrong. It is just embarrassingly incomplete. A star is not a thing. It is a process, a living argument between two forces that never stops, not for a single second, for millions or billions of years. At the core of every star, gravity is pulling inward, trying to collapse the whole structure into a point. But the star is also fusing hydrogen into helium at temperatures so extreme that the energy released pushes outward with equal ferocity. These two forces meet in the middle and cancel out, perfectly and continuously, in a balance so precise it makes engineering look accidental. Physicists call it hydrostatic equilibrium. It is, in every real sense, the heartbeat of a star. When the heartbeat holds, the star lives. When it falters, the star dies. And how it dies depends entirely on how heavy it was in life. A star like our sun burns for about 10 billion years, and it is already halfway through. When its fuel runs low, it will swell into a red giant large enough to swallow Mercury, then Venus, and possibly the Earth, then gently shrug off its outer layers and fade into a cooling ember called a white dwarf. That is a quiet death, almost dignified. But the universe does not always do quiet. A star 8, 10, 20 times heavier than the sun burns through its fuel in mere millions of years. And when its core finally runs dry, gravity wins the argument in less than a single second. The outer layers slam inward, rebound, and detonate in a supernova so bright it briefly outshines 100 billion stars. And what that explosion leaves behind is the fact I want you to sit with tonight. Sometimes the crushed core becomes a neutron star, a sphere about the size of a city, holding the mass of two suns, its atoms broken so completely that electrons and protons have merged into pure neutrons packed with no space between them. A single teaspoon of that material would weigh about 1 billion tons. Not a pound, not a ton. 1 billion tons, the weight of a mountain, pressed into the volume of a sugar cube. A marble of that substance would outweigh every human being on the planet combined. And these are not theoretical monsters. We have found them. They spin, some of them hundreds of times per second, sweeping beams of radiation across space like a lighthouse. When the first one was discovered in 1967, its pulses were so precise and so regular that astronomers half-seriously labeled the signal LGM-1, Little Green Men, wondering if it might be a message. It was not aliens. It was something stranger, the corpse of a star, keeping time more accurately than the finest clock human hands have ever built. To feel just how dense that truly is, try one more comparison. Gravity on the surface of a neutron star is so overwhelming that if you could somehow stand there, you would be flattened instantly. Thinner than a sheet of paper, a single marshmallow dropped onto its surface would strike with the force of a large bomb. This is what gravity does when it finally wins, when there is nothing left to hold it back. And every one of these objects began as a shining star, not so different from the ones you will see tonight. The sky is full of these hidden extremes, spinning silently in the dark, the ashes of suns that burned out long before you were born. And these stellar corpses do something useful for us, too. Because their pulses are so astonishingly regular, astronomers now use them as clocks scattered across the galaxy, a natural navigation system written into the sky. By listening to how the timing of many pulsars shifts together, ever so slightly, scientists can detect the faint ripples of gravitational waves washing through our entire corner of the universe. Waves stirred by black holes far larger than any single star. The dead stars have become our instruments. The universe, it turns out, left its most precise timekeepers lying in the wreckage of its most violent deaths, and we have learned to read them. But a neutron star, as extreme as it is, still holds a shape you can picture. When the dying core is heavier still, gravity does not stop there. It keeps winning, past every limit, into a place where direction itself stops existing. There is a moment when you look at an image of a black hole for the first time when something ancient in your brain sends up a quiet warning. Not quite danger, something older than that, the feeling of standing at the edge of something that does not care whether you exist. And that feeling is correct. A black hole is not a hole. That is the first thing to unlearn. It is not an absence, not a gap where something used to be. It is the opposite, presence taken to its absolute extreme. It forms when gravity becomes so total that nothing, not a rocket, not a beam of light, not information itself can escape. Einstein's theory of general relativity, published in 1915 and confirmed again and again in the centuries since, describes gravity not as a force pulling on objects, but as a bending of space and time. Near a black hole, that bending becomes so severe that space folds inward and refuses to come back out. At its center lies another singularity, a point where the equations break down and simply shrug. The boundary around that point is called the event horizon, and this is where it becomes almost unbearable to imagine. The event horizon is not a surface. You could not stand on it or feel it beneath your feet. It is a threshold drawn in the fabric of space-time, a line of no return. Cross it, and the roles of space and time trade places. In everyday life, you can move freely through space, but only forward through time. You cannot stop tomorrow from coming. Inside a black hole, the mathematics says the center becomes as unavoidable as tomorrow. Falling toward it is no longer a direction you can refuse. It is simply the future, arriving no matter which way you turn. For a long time, these were only equations, elegant and troubling, on a physicist's page. Then, in 2019, humanity did something that should never be taken for granted. Using a network of telescopes spread across the entire planet, working together as a single eye the size of the Earth, we captured an actual image of a black hole, a dark circle ringed by a halo of glowing matter 55 million light-years away. We had photographed the shadow of a place from which nothing returns. A few years later, we saw the one at the center of our own galaxy. Because there is one sitting at the heart of almost every large galaxy, including ours, it is called Sagittarius A star, and it holds the mass of 4 million suns compressed into a region smaller than our solar system. The entire galaxy turns slowly around it. You are, at this very moment, quietly circling a black hole, completing one orbit roughly every 230 million years. And yet, for all their terror, black holes are not only destroyers. When two of them collide, they send ripples through space-time itself, gravitational waves, real distortions in the geometry of space, passing through walls and planets and human bodies alike. In 2015, we finally built instruments sensitive enough to hear one. The universe had been speaking that language the entire time. And there is one detail about falling in that even the textbooks tend to rush past. If you drifted across the event horizon of a large black hole, you might feel nothing unusual at the moment you crossed it. No wall, no alarm, no sensation of a line being passed. Only later would gravity begin to pull harder on your feet than on your head, stretching you slowly, then faster, into a long, thin thread, a fate physicists have given the almost gentle name spaghettification. Stranger still, someone watching from a safe distance would never see you cross at all. To them, you would appear to slow, redden, and freeze at the edge forever. Two people, one event, two completely different truths, and neither of them wrong. That is the kind of place a black hole is. And black holes may hold one final surprise, one that turns their whole story on its head. The physicist Stephen Hawking showed that they are not perfectly black after all. At the very edge of the event horizon, where that restless vacuum is forever flickering, a black hole slowly leaks the faintest trickle of energy into space. Given an amount of time so vast it makes the current age of the universe look like a single breath, even the greatest black hole will evaporate completely, dissolving back into the emptiness it came from. The most unstoppable objects in existence are, in the very longest view, temporary. They take and take and take, and then, unimaginably slowly, they give it all back. And that slow turning of a whole galaxy points to a deeper mystery, because most of what holds these galaxies together is something no telescope has ever seen. Everything we have marveled at so far, every star, every nebula, every black hole, every galaxy, all of it together makes up less than 5% of the universe. 5%. The rest, the overwhelming, almost insulting majority of everything that exists, is something we cannot see, cannot touch, and cannot yet explain. We have given it names. We call it dark matter and dark energy. But naming a thing is not the same as understanding it. Consider how astronomers first suspected it. Picture a merry-go-round. The children at the edge must move faster than those near the center to keep up. A galaxy should work the same way, the outer stars orbiting slower than the inner ones. But when astronomers actually measured the rotation of galaxies in the 1970s, they found something deeply wrong. The outer stars were moving just as fast as the inner ones. The galaxies were spinning as if held together by some vast invisible scaffolding of mass, matter that gives off no light and shines in no telescope. This dark matter appears to make up about 27% of the universe. It does not emit light or absorb it. It slips through ordinary matter almost as though ordinary matter were not there. Right now, dark matter particles may be streaming through your body, through the floor, through the whole Earth, without touching a single atom. We have never once caught one directly. We know it is there only by what it does to what we can see, the way it bends the light of distant galaxies, the way it shapes the great cosmic web that visible matter clings to. We see the footprints, never the foot. And dark matter, strange as it is not the strangest thing here. In 1998, two independent teams measured distant exploding stars to see how quickly the universe's expansion was slowing down. Gravity should be applying the brakes. Instead, they found the opposite. The expansion is speeding up. Something is pushing space itself apart faster and faster, and it fills roughly 68% of everything that exists. We call it dark energy because we had to call it something. We do not know what it is, where it comes from, or whether it will hold steady or one day change. So here is where that leaves us. The universe is mostly something we cannot see, running on a fuel we cannot identify, expanding toward a destination we cannot yet predict. And yet, this is the part worth holding on to. We know this. We figured it out. With telescopes and mathematics and a willingness to follow the evidence into deeply uncomfortable places, human beings looked out at a cosmos that is 95% invisible and said calmly, "We can tell something is there." To measure the exact size of your own ignorance is a rare and noble thing. The greatest questions are still open, still waiting, perhaps for a mind not yet born. And we have even learned to photograph the invisible, in a way. When the light from a distant galaxy passes by a great clump of unseen dark matter, that light is bent, exactly as Einstein said mass should bend it, curving around the invisible mass like light through a lens. By mapping how those distant galaxies appear stretched and warped, astronomers can draw the outline of matter they cannot see at all, the way you might trace the shape of a person standing behind a frosted window. We have made maps of the invisible scaffolding of the cosmos. We cannot say what it is, but we can show you quite precisely where it lies. And dark matter did something for us long before we could map it. In the young universe, its invisible gravity was the scaffolding that everything else was built upon. Ordinary matter, the stuff of stars and planets and people, was too thin and too scattered to gather on its own. It was dark matter, pulling quietly in the background, that first drew the gas together into the clumps that would ignite as the earliest galaxies. Without that unseen framework, the cosmos might have stayed a smooth, formless haze forever, with no stars, no worlds, no one to wonder about any of it. The thing we cannot see may be the reason there is anything to look at all. And if the very fabric holding the galaxies is stranger than it looks, then so is the fabric everything rests upon, because time and space themselves are not at all what you think they are. Here is a question that sounds simple until you sit with it. When you look at a star, when are you seeing it? Not where it is, when it is. Because light, for all its speed, is not instant. It travels, and the distances of space are so vast that by the time starlight reaches your eye, it has been on a journey longer than you can easily imagine. Light moves at about 186,000 miles every second, a speed that feels like magic. Yet the light from Proxima Centauri takes more than 4 years to reach us. When you see it, you are seeing it as it was 4 years ago. Look further out, and you look further back. There are stars in your night sky whose light left on its journey before you were born. And through a telescope, galaxies whose light has crossed millions, even billions, of years to arrive tonight. Some of those distant stars have already died, but their light is still in transit, still arriving, so we continue to see them shining as though nothing has changed. Now let that idea settle, because it means you are never really looking at the universe. You are looking at the memory of the universe. The night sky is not a photograph of the present moment. It is a layered painting of many different pasts, all reaching your eye at once. The recent past of the moon, seen as it was a single second ago, and the deep past of distant galaxies, seen across the gulf of eons. And it goes deeper than distance. In 1905, Einstein showed that time and space are not separate things, but woven into a single fabric, space-time, and that fabric is not rigid. It bends under mass, and because time is part of it, time bends too. The closer you are to a heavy object, the slower your clock runs. This is not a feeling. It is measured. The GPS satellites that guide you to an unfamiliar address tick faster than clocks on the ground because they sit higher in Earth's gravity, and if engineers did not correct for that tiny difference, your navigation would drift miles off course within a single day. Push it to the extreme and it becomes almost dreamlike. Near a black hole, someone watching you fall would never quite see you cross the edge. They would watch you slow, redden, and freeze at the threshold, suspended forever, while for you, time runs on as normal. Speed bends the clock too. Travel close to the speed of light, and years could pass for you while centuries pass on Earth. This is why physicists say the past is never truly deleted. The universe carries its history forward at the speed of light, and every clear night, that history is hanging silently over your head, waiting to be noticed. There is a famous thought experiment that makes this real. Imagine two twins. One stays home on Earth. The other boards a fast spacecraft, races out toward a distant star at close to the speed of light, and returns. When the traveler steps off the ship, they are genuinely, physically younger than the twin who stayed behind. Not through any trick or illusion, fewer seconds have actually passed in their life. The universe, in effect, handed them extra time for moving quickly through space. This is not science fiction. It has been confirmed by flying precise atomic clocks on aircraft and comparing them to identical clocks left on the ground. The traveling clocks come back very slightly behind. Time is not the fixed drumbeat you always assumed. It bends, and it bows, and it keeps no single master. And there is a quiet consequence of this that changes how you might think about the past itself. If time is a dimension, woven into the same fabric as space, then, in a strange but real sense, the past is not erased when it ends. It is simply a place in that fabric you no longer stand. Right now, somewhere out in the dark, the light of events long finished is still traveling, still carrying those moments outward, real in the physics of the universe, even though they are over for us. The cosmos does not delete its history. It sends it onward at the speed of light, in every direction, forever. Nothing that ever happened is entirely, completely gone. And if starlight can carry the past across such distances, then something even harder to feel is happening right now. An invisible traffic pouring straight through your body this very second. Hold up your hand and look at it. Solid, warm, familiar. It has carried you through your whole life. Now understand that at this exact moment, an invisible storm is pouring through that hand, through your bones, your heart, your eyes, and it does not so much as brush against you. You are being passed through constantly by ghosts. They are called neutrinos, and they are among the most numerous particles in the entire universe. They are born in the hearts of stars, including our own sun, where nuclear reactions produce them in staggering numbers. Every second, roughly 100 trillion of them stream out of the sun, cross 93 million miles of space, and pass through your body without stopping. Awake or asleep, day or night, it never pauses. At night, they simply travel up through the entire Earth first, and then through you. Why do you never feel them? Because neutrinos almost never interact with anything at all. To a neutrino, solid matter is mostly empty space, and it slips between the atoms as though they were not there. A neutrino could pass through a wall of solid lead a light year thick and still have a fair chance of coming out the other side untouched. To catch even a handful, scientists build enormous detectors deep underground, great tanks of fluid buried beneath mountains, shielded from everything except these ghostly travelers. And this connects to something the last chapter only hinted at. When you press your hand against a table, you have never actually touched it. What you feel is the electrons in your skin repelling the electrons in the surface. No part of you has ever made contact with any part of anything else. The atoms you are made of are themselves almost entirely empty. Scale a single atom's nucleus up to the size of a marble, and the nearest electron would orbit roughly a kilometer away, with nothing in between. You are, in the most literal physical sense, almost completely empty space. And yet you feel entirely solid, entirely real. When we do manage to catch a neutrino, it tells us secrets we could learn no other way. Because these particles escape the sun's core almost instantly, they carry a live report from a place no telescope can ever see directly. In 1987, detectors on Earth caught a burst of neutrinos from an exploding star in a neighboring galaxy, arriving hours before the light of that explosion became visible in our skies. We felt the death of a distant star through its ghosts before we ever saw it shine. That single event opened an entirely new way of looking at the cosmos. For all of human history, we studied the sky with light alone, the visible glow of stars, and later, the radio waves and X-rays our eyes cannot see. But light can be blocked, absorbed, scattered by dust and gas. Neutrinos are stopped by almost nothing. They come to us straight from the hidden interiors of stars and explosions, from places light itself cannot escape. We have built, in effect, a new kind of eye, one that sees not by light, but by these silent, weightless travelers. And that eye is pointed, day and night, at the deepest furnaces in the universe. And neutrinos carry one more quiet wonder. For years, physicists were puzzled that we seem to catch too few of them coming from the sun, only about a third of the number the equations demanded. The particles were not missing, they were changing. On their 8-minute journey from the sun to the Earth, neutrinos shift from one type into another and back again, transforming in flight, which also revealed that these near-nothing particles carry the tiniest whisper of mass after all. Think of that. A particle so faint it can cross a light-year of solid lead, and yet it quietly changes its very identity on the way to your body, and we found a way to prove it. So the sky is crowded beyond counting, with stars, with particles, with invisible mass. Which makes the next question stranger than it sounds. If it is all so full, then why, when you look up at night, is the sky dark at all? Let me ask you something children ask and adults forget to wonder about. Why is the night sky dark? It sounds too obvious to bother with. The sun has set, so of course it is dark. But that easy answer hides one of the deepest puzzles in the history of astronomy, one that troubled brilliant minds for centuries. Here is the problem. If the universe were infinitely old and infinitely large, and if the stars were spread more or less evenly throughout it, then no matter which direction you looked, your line of sight should eventually land on the surface of a star. Every point in the sky should blaze with light. The night should be as bright as the surface of the sun. This is known as Olber's paradox, and its answer is not laziness of the eye. Its answer is the history of the universe itself. The night is dark for two profound reasons. First, the universe is not infinitely old. It had a beginning, 8 billion years ago, so the light from the most distant regions has not had time to reach us yet. And second, the universe is expanding, stretching the light from the farthest galaxies until it slips beyond the range our eyes can see. The darkness between the stars is not empty of light. It is full of light we simply cannot perceive, light dimmed and stretched by the very growth of space. And this raises a quieter, gentler question. If we could gather all the light of every star in the universe and blend it into a single shade, what color would the cosmos be? Astronomers actually did this. They averaged the light of hundreds of thousands of galaxies, and the answer surprised even them. Taken as a whole, the universe is not blazing white and not deep blue. It is a soft, pale beige, a warm, milky tone. Someone gave it a name, cosmic latte. There is something deeply humbling in that. All the violence of exploding stars, all the fury of colliding galaxies, all the fire of a trillion suns averaged together, it comes out as a quiet, warm, almost domestic color. The universe at its grandest scale is not harsh, it is soft. And the darkness that lets you sleep at night is not a lack of the cosmos. It is a message from its age and from its endless, patient expansion. And that expansion is not a guess. You can see its fingerprint written directly in the light of distant galaxies. As space stretches, it stretches the light traveling through it, shifting its color toward the red end of the spectrum, the way the pitch of a passing train drops as it moves away from you. The farther away a galaxy is, the more its light is reddened, and the faster it is receding. It was this simple, careful observation made about a century ago that first told us the universe is not static but growing. The darkness of the night sky and the reddened light of far-off galaxies are two halves of the same quiet truth. Everything is drifting apart, gently, in every direction, all the time. And that gentle drift has a lonely implication far in the future. Because the most distant galaxies are receding faster and faster, their light is being stretched further and further until one day it will fade entirely beyond our reach. Astronomers who live billions of years from now, if any do, will look out and see only darkness where trillions of galaxies once shone. The evidence of the wider universe will have quietly slipped over the horizon of what can be seen. We are, in a sense, living in a privileged moment, one of the few eras when the sky still tells the truth about how vast everything really is. That, too, is a reason to look up now, while the looking is still good. That softness is a fine place to catch your breath, because we are about to leave the calm behind and visit worlds so strange that the weather itself rewrites what you thought a planet could be. For most of human history, we knew of only a handful of worlds, the planets of our own solar system. Then, beginning in the 1990s, we started finding others circling distant stars. We call them exoplanets, and when the Kepler Space Telescope scanned a tiny slice of the sky, less than 1% of it, it found thousands in just a few years. Extrapolate across the galaxy, and the number becomes grotesque in its scale. Hundreds of billions of worlds in the Milky Way alone. And what we have found out there is stranger than anything the old storytellers dared to invent. Consider a planet where it rains diamonds. On the giant worlds of Neptune and Uranus, and on certain distant planets larger still, the pressure and heat grow so extreme that carbon in the atmosphere is squeezed until it hardens into diamond, falling like hail through the crushing depths. What would be a treasure beyond imagining on Earth is, on those worlds, simply the weather. Consider a planet hotter than many stars, orbiting so close to its sun that a single year lasts only hours, where astronomers believe it may rain molten glass or molten iron, blown sideways by winds faster than any hurricane. And consider the opposite extreme. Rogue planets, cast out from the systems where they were born, wandering the galaxy alone in total darkness, with no sun and no year, frozen and lightless for ages without end. Each of these worlds began as the faintest signal in our instruments, a tiny dimming of a star as a planet crossed in front of it, or the smallest wobble in a star's motion. From clues that small, patient scientists reconstructed entire worlds. Their size, their heat, sometimes the chemistry of their skies. We have never seen these places with our own eyes, and yet we know they are there as surely as we know the ground beneath our feet. But the strangest world in this chapter is the one you are sitting in right now. Because you are not just alive in the universe, you are made of it, literally. Every calcium atom in your bones was forged inside a star that died before our sun existed. The iron in your blood carrying oxygen to your brain so you can follow these very words was created in the heart of a stellar explosion so violent it briefly outshone entire galaxies. Stars do not just burn, they build. Deep in their cores they fuse hydrogen into helium, helium into carbon, carbon into oxygen, on and on up the ladder of elements, until they reach iron, and the furnace fails, and the star collapses and scatters everything it ever made across space. Those atoms drift for millions of years through the cold dark, until gravity gathers them into a new cloud. A new star, new planets, and on at least one of them, chemistry became biology, and biology became something that could look up and wonder where it came from. That is you. And your atoms have had other lives. The carbon in your hand may once have been part of an ancient ocean, or a different star in a different corner of the galaxy. You do not own your atoms. They are passing through. You are a temporary arrangement of the universe, holding itself together just long enough to look around. And follow that chain back far enough, and something remarkable appears. The atoms in your body were forged in stars. Those stars were born from the remnants of earlier stars, and the very first stars formed from the hydrogen left over from the Big Bang itself. Which means the line connecting you to the beginning of time has no break in it anywhere. There is no gap. No moment where the cosmic story paused and something separate began. The same physics that lit the first stars is the physics holding your cells together as you listen. You are not a visitor to the universe, watching from outside. You are the universe, one of its more recent and more complicated arrangements, turned around at last to look at itself. And the atoms carrying out that quiet miracle are almost unthinkably old and well-traveled. The hydrogen in the water you drank today has existed since the first minutes after the beginning of time. The oxygen in your next breath was cooked inside a dying star and flung across the galaxy before our sun was ever born. These atoms have been part of oceans, of stone, of other living things, long before they were briefly, temporarily, you. When your body is finished with them, they will move on again, into soil and air, and in time, into new stars not yet formed. You are not a possessor of your atoms. You are a passing arrangement of them, a pattern the universe is holding, for a little while, in the shape of a person. And if you are the universe looking at itself, then the oldest question of all becomes unavoidable. Across all those numberless worlds, is anything else out there looking back? Start with the arithmetic, because it seems to settle the matter before you even ask. The Milky Way holds 2 to 400 billion stars, and astronomers now estimate that most of them have planets. Many sit in the habitable zone, not too hot, not too cold, the narrow band where liquid water could pool on a surface. Now zoom out. The Milky Way is one galaxy among roughly 2 trillion. Take even the most cautious guess for how rare life might be. Run it across that many worlds, and the numbers scream that we should not be alone. And yet, silence. No signals, no visitors, no confirmed contact of any kind. This is what the physicist Enrico Fermi noticed in 1950, over lunch, when the talk turned to alien life. He asked, with disarming simplicity, "Where is everybody? If the universe is so vast and so old, and the ingredients for life so common, why have we heard nothing at all?" That question became the Fermi paradox, and it has never been resolved. The proposed answers fall into 2 moods. The first is almost gentle. Perhaps they are out there, and space is simply so enormous that conversation across it is nearly impossible. A civilization 1,000 light-years away that noticed our radio signals would be hearing broadcasts from before most living people were born. Reply instantly, and we would not hear back for 2,000 years. Communication across the cosmos is not slow. It is geological. The second mood is harder to shake. The idea of a great filter, some step on the road from simple chemistry to a star-faring civilization so brutally unlikely that almost nothing crosses it. The unsettling question is whether that filter lies behind us, which would make us rare and precious survivors, or somewhere ahead. There is a further possibility, quieter and stranger. Maybe we are simply looking for the wrong thing. Life on Earth is carbon-based and water-bound, tuned to a narrow band of temperature and pressure, but those are Earth's conditions, the ones that made us. And most of cosmic history happened before Earth even formed. The universe had a 9 billion year head start. A civilization that old would not be a few centuries ahead of us. It might stand as far beyond our understanding as we stand beyond a single bacterium. We could be swimming in the evidence and simply lack the eyes to recognize it. So the silence does not hand us an answer. It hands us a weight. Either we are something extraordinarily rare, perhaps among the very first, which makes every moment of human awareness a kind of cosmic treasure worth protecting. Or the universe is quietly full of life we are not yet equipped to see. What we know for certain is this: physics did not require life. The equations did not demand it. And yet here you are, made of the ash of dead stars, asking whether anything else out there is doing what you are doing tonight, breathing, wondering, looking up. That question may be the most human thing there is. People have tried to put numbers to it. Decades ago, an astronomer named Frank Drake wrote down a now famous equation, not to give a final answer, but to organize the question, to lay out everything we would need to know to estimate how many civilizations might be out there. The honest truth is that we still cannot fill in most of its terms, and some thinkers offer a darker reading of the silence. One idea, drawn into popular imagination by a novelist, suggests the universe may be quiet not because it is empty, but because any civilization that announces itself risks becoming a target. So the wise ones stay hidden. It is a bleak picture, and it may well be wrong. But it is not obviously wrong, and that is exactly what makes the silence press on us the way it does. And we have not simply sat and waited. For decades, we have listened. sweeping vast radio telescopes across the sky, straining for any signal that carries the unmistakable fingerprint of intention rather than nature. We have sent messages of our own, golden records bolted to spacecraft now drifting past the edge of the solar system, carrying the sounds of a whale, a heartbeat, a greeting in dozens of languages, into a silence that stretches for light years. Perhaps no one will ever find them, perhaps someone already has. Either way, there is something profoundly human in the gesture, in a species so young reaching out into the dark, unwilling to assume it is alone, unwilling to stop asking. And whether the sky is crowded or empty, every civilization that ever existed shares one destination, because the universe itself is moving, slowly and certainly, toward an ending we can already describe. We have spent this hour looking outward and backward, into the depths of space, into the distant past. Now we turn to the one direction we have not yet faced. Forward. Toward the end, because everything that begins must, in some fashion, conclude, and the universe is no exception. The question was never whether it ends, but how. It begins with the stars going out. Right now, the cosmos is ablaze, hundreds of billions of galaxies pouring light into the dark, and it feels permanent. It is not. The stars are burning through a finite supply of fuel, and across spans of time so vast they make the present age of the universe look like a single heartbeat. They will flicker out one by one. New stars will stop forming. The galaxies will become graveyards of cooling embers, drifting further and further apart, carried by that mysterious dark energy into isolation and dark. For an almost unspeakable stretch of time after that, the last active objects will be the black holes. And even they are not immortal. Stephen Hawking showed that they slowly leak energy at their edges and, over spans written as 10 raised to unimaginable powers, evaporate entirely, the most massive objects in existence dissolving, particle by particle, back into the quantum foam from which everything came. When the final one goes, what remains is a thin, even sea of particles, spread so far apart that no two will ever meet again. Physicists call this the heat death, the victory of entropy. Not fire, not ice, but a silence so complete that the very word empty stops having anything to be empty of. There are other possible endings, a big rip that tears space apart, a big crunch that collapses it back inward, but each carries the same quiet truth. The universe is not eternal. There is even a stranger possibility that keeps some physicists up at night, called vacuum decay. It rests on the idea that the emptiness we spoke of at the very beginning of this hour, that humming, restless vacuum, might not be perfectly stable. If it is not, then somewhere, at some random point in space, a tiny bubble of a more stable emptiness could one day form and rush outward at the speed of light, quietly rewriting the laws of physics as it went. You would never see it coming. It would arrive before any warning could. It is worth naming, and then worth setting gently down, because like all these endings, it lies so unfathomably far away that no human worry can reach it. These are not fates to fear. They are the final chapters of a story almost too large to tell. And step back from all of it for a moment, because the time scales here are strangely comforting. The heat death, the last flicker of the last black hole, lies so many years in the future that the number cannot be written in any way a human mind can feel. Compared to that endless cold, the entire age of stars, the whole chapter in which planets form and oceans gather and life becomes possible, is a brief, brilliant flash near the very beginning. And we are inside that flash, not near its end, near its bright, warm start. Of all the moments the universe will ever have, you were handed one of the rare few in which there is light to see by, and eyes to see it, and time enough to wonder why. And here, at the close, is what I hope you carry with you, because it is the opposite of despair. The era of stars, the whole warm, bright chapter in which chemistry happens and life is even possible, is a razor-thin sliver compared to the endless cold that follows. And we are inside that sliver, right now. This is the loud part. This is the warm part. Out of all the ages of the universe, you happen to be alive in the one where the stars still shine, where the light is still legible, where a mind exists to understand any of it. That is not a small thing. That might be the most extraordinary thing we know of anywhere. The universe does not hand you meaning, but it hands you the stage and the light and the time to make some. You are hydrogen and helium from the first minutes of creation, rearranged over 14 billion years into something that can wonder about hydrogen and helium. Let that make you braver, not smaller. So if this hour among the stars gave you even one moment of that quiet wonder, let me ask a small thing of you in return. Take a second to subscribe to this channel so we can keep making journeys like this one together in the evenings to come. Leave a like on this video, it genuinely helps more curious minds find their way here. And most of all, tell me in the comments below, which fact tonight stayed with you the longest, and what corner of the universe should we explore next? I read every one, and your questions often become the next journey we take. Then before you sleep, go outside and look up. The silence is not empty. The past is still shining. Your atoms were forged in dying stars, and the universe, vast, patient, and strange, is waiting for you to keep wondering. Thank you for spending this hour at the edge of everything. Until next time, keep looking up.